4th of July 2012, memorable date, there was a big announcement at the CERN laboratory that 2 experiments at the Large Hadron Collider, ATLAS and CMS, had detected a particle known as the Higgs particle. And there was a big celebration and party and people letting their hair down. The evidence is kind of thin. You have to look at this curve there and agree that the data points are not just fitting on the smooth curve, but there's a little bump in them. And likewise over on the right. So it was statistically, you had to be a bit casuistical and talk about 5 standard deviations and things. But the fact that both experiments saw this bump at the same place and 125 GeV was a big point in its favour. And incidentally, in the 5 years that have gone by since then, there have been more data. These peaks have got bigger and more convincing, and the discovery is definitely confirmed. If you worry about what a GeV is, don't. It's just a way of measuring the mass of particles, because you can't really talk about pounds and ounces and kilograms. If you insist on worrying about the definition of a GeV, it's about the same as the mass of a hydrogen atom, so think like that. Now, there's about over 2,000 people working on ATLAS and about 3,000 working on CMS. I am not one of them. I work on the LHCb experiment on the bottom. So although I am not one of the authors of the Higgs discovery papers, I have authored a very large number of papers over the years entitled Limits on the Higgs Mass, Search for the Higgs Mass, and other failures to discover the Higgs. So it and I are old acquaintances. I will not say friends, but certainly acquaintances. And I think this qualifies me to try and explain to you what this fuss is all about, because after all, particle physicists discover particles quite often. What is so special about this one? And it is special, and not just because the New York Times refers to it as the God particle. It is special, and I want to explain to you why, because I think the story of the Higgs is one of the big intellectual and cultural developments of the second half of the 20th century and early 21st century. It's up there with the moon landings. And so it should not just be kept to the particle physicists. It belongs to everybody. And just as you can enjoy music without understanding musical notation, you can enjoy watching a football match even if you've never played football, there's no reason why you shouldn't understand and enjoy something about particle physicists, even if you've never seriously studied the subject. So I am going to attempt to do that. Please help me. I have limited myself to just one equation. It was quite a strain. Don't worry when we get to it. So the story of the Higgs, it's been a long time. It was first predicted in about 1964 when the paper was published. It was promptly ignored for about 10 years. But in the 70s, it got picked up and people started looking for it seriously. And we looked for it. I looked for it in 2 experiments at Petra and failed to find it. That was at 30 GeV in the 1970s out in Hamburg. Then I went to Geneva and didn't find it at LEP, up to 200 GeV. I didn't go to Chicago at the Tevatron, but they didn't find it there either in the 1990s. So it's got a long history of people looking for it really, really seriously. Much, time and money and graduate students have been sacrificed in the attempt to find this particle. And it was popularized by Lederman's book, that in 1993, and many other books, but his in particular was entitled The God Particle. Partly because putting God in helps you sell books, but there are other reasons as well. So particle physicists are looking at the fundamental question of what are we made of, taking it down and down and down. We've known for 200 years or so, ever since Dalton and friends, that we are all made of atoms. If you like to say nothing but atoms, you can say nothing but atoms, or you can just say we are made of atoms. So there is the periodic table again. which is fine. The chemists are happy, but some smartass comes and says, well, what are atoms made of? And we know for about 100 years that atoms are made out of a nucleus surrounded by a cloud of electrons, and that nucleus is made up of protons, which are positively charged, and neutrons, which are negatively charged. That is the conventional... No, thank you, just testing. Neutrons, which are neutral, yeah. That is the standard picture of an atom. Technically, there are so many things wrong with it, I wouldn't know where to begin, but it's clearly drawn by an artist rather than a physicist, so it's all wrong, but it's a good picture. And we've also known for about 50 years, I suppose, what are protons and neutrons made of? Well, protons and neutrons are made out of quarks. They're made out of up quarks and down quarks. Up quarks are positive with a charge of plus 2/3. Down quarks are negative, I got that right, with a charge of minus 1/3. And a proton is made out of 2 up quarks and a down. 2/3 plus 2/3 minus 1/3 is 1. And neutrons are made of 2 down quarks and an up. Minus 1/3 minus 1/3 plus 2/3 equals 0. So that's fine. Everything is made of atoms. Atoms are made out of protons and neutrons and electrons. Protons and neutrons are made out of quarks. So the whole universe is made up of these 3 fundamental building blocks. It's like you've got a Lego set and there's only 3 different sorts of pieces in it, or Meccano if you're a bit older. So please enjoy that nice simple picture, because it's not going to stay nice and simple for very long. In the 1930s, it was suggested there might be another particle called the neutrino, discovered in the 1950s. It's a bit like an electron, but it's neutral. So we now have 4 particles. Some wise guy discovered the muon, which is just like an electron, but more massive, 200 times more massive. For no apparent explicable reason, it's just a big version of the little guy. Oh, and it has its own neutrino, which somehow manages to be different from the electron neutrino. And there is also a quark called S for strange, discovered in Manchester, or rather the particles which we now know contain it were discovered in Manchester. And in the 1970s, when I was just about becoming aware of things, the charm quark was discovered, a heavier version of the up quark. So it looks as if we've got the up and down quarks that make protons and neutrons, and the electrons and the neutrino, and this is just duplicated, everything the same but a bit heavier. Actually, it's not, it's triplicated. One of the things we discovered is that there's an awful lot of 3s in this business. 2 quarks known as T and B, which sometimes stand for truth and beauty and sometimes for top and bottom, depending on how poetic you're feeling at the time. A particle called the tau, which is like a very heavy electron but has its own neutrino. So we have 12 fundamental particles. Luckily, we can categorize them. There are the 2/3 quarks, the minus 1/3 quarks, down-like and up-like, the charged leptons, the electron and its higher relations, and the neutral leptons. And we call these 3 generations, though that's just a word which doesn't actually mean anything. It's a useful way of talking about it. So there are 12. Actually, no, there are 24, because each of these particles has an antiparticle with the opposite charge and the same mass. So although we only need 3 fundamental particles, nature or providence or what have you has given us 24 of them. So those are the players. How do they interact? How do they talk to each other? And David mentioned the 4 forces earlier. I'm glad of that. There are not just one sort of interaction, but 4 of them between these particles. 2 of them we know about, 2 of them are new. One that we know about is the electric magnetic force. They're the same thing, charges attract and repel, currents, magnetic fields and so forth, fine. One of them we know about is gravity, but gravity is so weak it doesn't really affect individual small particles, and anyway, we don't really understand it at this level, as has been referred to earlier, so I'm not going to talk about it very much. The other two forces are specific to nuclear and subnuclear physics, and with a total lack of imagination, these are known as the strong nuclear force and the weak nuclear force, because one of them is strong and one of them is weak. The strong one is the force that confines these quarks, which makes three of them, not two of them, not four of them, stick together to form a proton or neutron or what have you. And the other is the weak nuclear force, which is an interaction which allows quarks to change type. It's what gives you nuclear beta decay, allows electrons to produce neutrinos, and vice versa. Much weaker by factors of many billions than the strong force. Okay, so there are the four forces. Now I want to sort of back off a bit and think about, I've said we understand the electric force, the magnetic force. Fine. So here are two. I've tried to draw it. It's sort of survived the keynote to parabolic to keynote transition. You have two charged particles, say positive. They move together. They repel each other. They deflect off. Fine. You can see the picture. And if you ask a A-level student, there may be some A-level students here, but don't worry, I'm not going to ask you. If you ask an A-level student, why do these charges repel each other, they will say Coulomb's law. There is an action at a distance. I did write down the formula, F equals Q1, Q2 of 4 pi epsilon naught r squared, but then I remembered I wasn't supposed to use equations, so I took it out again. But there is an inverse square law reaction force between them. Fine. If you were to ask a physics undergraduate, why do these particles repel each other, then they would say Gauss's law. The particle produces an electric field. The divergence of the electric field is the charge contained, and this electric field influences the other particle. So you've got a more sophisticated explanation which incorporates the earlier explanation and does not contradict it. It's just fuller, more complete, contains more, and gives you a bigger picture. If you ask a graduate physics student, you probably have to choose them quite carefully, why is there a force between the two particles? They would say it's because of the Feynman rules. These particles, as they go, can be thought of as exchanging virtual photons, and this exchange of virtual photons produces a force between them. And the picture everyone draws is something like this. If your particles are like two people each in a boat on a lake, and they're throwing a heavy ball between them, those are the virtual photons, then that will produce a repulsive force, and the boats will drift away from each other, and in the same way these particles will deflect away from each other. So the electromagnetic force is carried by virtual photons. And the same method, the same picture, works for all four forces. Electromagnetism carried by virtual photons, which have zero mass. The strong force, confining quarks within nucleons, confining nucleons, protons and neutrons within the nucleus, is carried by gluons, which also have zero mass. The weak interaction is carried by a bunch of particles called W and Z, which have heavy masses. And gravity is presumably carried by zero mass gravitons, but as I say, I don't want to talk about gravity. So, four forces, four force-carrying particles. And it's a way of describing the force. You can put it into mathematics and it works, or you can just think of it as happening. Slight digression on mass, because I've mentioned it a bit. There are massive objects and there are less massive objects. And we experience mass in different ways through the, its inertia, difficulty of picking it up, impact you get when it strikes you, and so forth. And of course, all these ways are equivalent. You can just work through the arithmetic and one produces the other. Without saying any of these other ways is wrong, the fruitful way to think about mass at this point is through Einstein's E equals mc squared equation. That's my one equation. Okay, it was only that. And Hawking says you're allowed that equation without harming your book sales or audience participation or whatever. So the mass of a particle is the minimum energy you could give it. If you want an electron, it's got a mass of 0.0005 GeV. You've got to put up at least 0.0005 GeV to make one, and they only come in pairs, so you'd have to produce 0.001. If you want a photon, on the other hand, photons are massless. You can have a photon with as little energy as you like. But for any massive particle, there's a certain amount you have to put up to make that particle at all before you start giving it any potential energy or kinetic energy or something like that. It's a bit like the door charge on a nightclub. You've got to pay up front before you do anything in the way of buying drinks or whatever. So mass here I'm going to use in terms of the basic energy you have to make the particle. Right, now please work with me on this slide, because this slide is the key point in particle physics, and if you understand this, you have really got it. So, suppose you want to design the rules for a universe. And this is the sort of thing that theoretical physicists like to do on their free afternoons. How would we like the universe to work? So you've got a nice blank sheet of paper, and okay, you think there should be some particles in it. So you can specify quarks, leptons, or whatever sort of particles there might be, and you can write down some equations of motion for them. They will be very boring equations of motion because we've just put in some particles, and all they're going to do is drift around and not even bump into each other or anything like that. Fine. Suppose, because it's our universe we're defining, and we can do what we like, suppose each of these particles has a number which we will call, for the sake of the argument, electric charge, which could be 1 or 0 or -1 or 27/3 or whatever you want for this particular particle. So we just stick a number on each type of particle. Fine. Now suppose you look at your theory and you see, can I identify some sort of symmetry in this theory I've written down? And symmetry here means I could make some change to the mathematics which doesn't change the physics and the output. And there's one obvious one in here. We could interchange the charges of the particles. We could call our electrons positive and our protons negative, for example, and that would not make any difference to the physics we were describing. Electrons would still repel each other because they had the same charge, even if it was positive. Electrons would still go round protons because they have opposite charges, even if this is negative positive, even if this is positive negative rather than negative positive. So there is, and it is in fact Benjamin Franklin's fault. It was he who arbitrarily decided, when he was doing his experiments back on relativity, that current flowed that way around a loop from positive to what he called positive to negative, and now we all know that it's really electrons flowing the other way, and there is this distinction between the flow of the current and the flow of the electrons, which has plagued us all ever since. He could have done it the other way around, and the mathematics would all have changed minus signs everywhere. The physics would still have been the same. So we found the actual the actual symmetry is a bit more complicated than that, but it does include this as a subset of it, so this is a valid example to use, even though it's not the whole story. But okay, you've got a symmetry. Then you decide that it would be nice if you could make one choice here and a different choice here. So we are in Hertford, we're just actually over the border between Cheshire West and Cheshire East. So we could say in Cheshire West, we will decide to have negative electrons and positive protons, and in Cheshire East, we will call the electrons positive and the protons negative. And within each half county, everything will still be fine. But of course, if you could try and describe matters at the boundary where your changeover in rotation is occurring, then things will go horribly wrong. So it will not work. Not surprisingly, you're making a very, very strong demand on your theory. Okay, you say, I like my theory, I like this symmetry. If I want to insist that this symmetry applies not just globally overall, but locally, making different changes in different places, maybe I can save that by introducing some extra terms into my equations of motion. So I add some extra terms, or you're doing this, it's your white sheet of paper, you add a few extra terms, as the minimal you can, to your equations of motion, which make this symmetry, which you've identified globally, also applicable locally. And it's just, you're just designing a universe, you can do this. And then when you look at those terms, what have you written down, and say, what do these correspond to? What you find is that these describe a force-carrying particle, a massless force-carrying particle. So if you say, I'm going to try and lay down some rules for electricity, electromagnetism, let there be charges, let the charges be kind of arbitrary in a mathematical way, which is sensible. Let this arbitrariness be not just an overall change, but a different change locally, which is a very strong requirement. Then to make that work, we have to introduce an extra particle, which is massless, which conveys the force, and we call it the photon. Let there be light. So this is the sort of game theoretical physicists like to do, and you may or may not be impressed. We start off with minimal assumptions, and the force particles drop out of them. We don't have to say there is electricity and there are electric forces. We say there is electricity and there is a symmetry principle. The forces drop out. So the key is that it doesn't just work for electric force, it also works for the strong force. You get gluons, and the gluons are also massless force-carrying particles, and you don't have to say, let's introduce gluons. You have to say, let's have some strong charges and a symmetry principle, which we will make local. Gravity is also a gauge theory, but I'm not going to talk about gravity, so I'll skip over that. However, for the weak force, you get a very nice theory, which just happens to be wrong. It predicts very firmly that we have three massless force-carrying three massless particles carrying the weak force. So, this was worked out about sort of 1950s, and there was a dedicated band of a few who kept going and saying, we think this is such a beautiful idea, we're going to try and persist with it, even though everybody knows that the mass of the W particles is not zero, it's 80 GeV or 92 GeV or something like that. Right. So, this is where the Higgs comes in. Higgs, in his 64 paper, says, Suppose there is a field, let's call it H. He actually calls it phi, but everyone else calls it H for Higgs. Right. There is some field defined everywhere. Suppose that this field interacts with all the other particles. We've got the quarks, the leptons, the W bosons and so forth, not the photons and gluons. And if you have a Higgs field, then oscillations about that Higgs field's equilibrium value correspond to Higgs particles. Now, so far, this is all absolutely standard stuff. Photons, electrons, quarks, they're all fields which interact with stuff, and if they oscillate and you excite them, you get particles. However, the fourth point is totally different. It says this equilibrium value is not 0, which it is for any sensible particle, but it's got some finite value. It's actually 246 in some units, but never mind. So there is a Higgsness everywhere. We are swimming in it, this non-zero Higgsness. We're like, and the discovery is like a group of fish who realise for the first time that they're swimming in water. There is this Higgsness there. And you say, well, why don't we feel it? Well, we do. We just don't realise that we feel it because we're so used to it. What happens is you combine your gauge symmetries with this Higgs field, and our three weak interaction bosons, which the gauge theory says have to be massless, they interact with this Higgsness. And that interaction with the Higgsness which is there gives them an energy, and that energy is an energy which you have to have if you want to make one of these particles. So it effectively is a mass. It looks like a mass, it smells like a mass, it quacks like a mass, it behaves like a mass, except it's acceptable to the gauge principle. It doesn't destroy the symmetry. And there's a wrinkle which says that W plus minus and the Z are a bit different, and it also, the quarks can change in the weak interaction because they're interacting through this Higgs field. So the Higgsness, which is everywhere, explains the masses of the W's, also the masses of the quarks and leptons as it happens, and the way they can change. And this is the first reason for Lederman and company saying this is like the God particle, because it is everywhere, it's ubiquitous, and because it does a whole lot of different stuff in all sorts of aspects of behaviour. The second reason goes back to the Big Bang. In the beginning, in the very beginning, I can't remember what fraction of a second it was, so don't ask me, the universe was very, very dense and it was very, very hot, and on David's energy versus time plot, it was right up there in the top corner. Lots of energy, very, very early time. And there were lots of particles, quarks and leptons and force carriers and what have you, and they were all massless, and it was all symmetric. The up and the down quarks were exactly the same. And so you have this initial prior state, very early in the innocent universe of perfect symmetry. But there is one particle which was more subtle than any of the others, and as it interacted with the other particles, and as it cooled down, instead of having an average value of 0, it broke the symmetry and produced this value of 246. Let me try and give you an illustration. Think of the letter U. Yeah? And suppose this is, the U is nice and symmetric, and if you've got a ball bearing or something in a U-shaped valley, and you drop it in, it will go to and fro and lose energy and end up in the middle. You're still nice and symmetric. Now suppose you've got a W, and we'll make it a sort of curly W with wobbles in. Yeah? The W itself is symmetric. You drop your particle in, it rolls around, up and down. It will eventually settle down in one side or the other. And then you have broken your symmetry, even though you've done nothing asymmetric to do it. So that's, the rest just follows on. So that's the point. Particle physicists are sometimes accused of being arrogant. If we are, it's not because we're cleverer than everybody else. We're just born that way. We can claim no credit for it. It's because we know the key to the universe. We know what it's all about. It's all about 3 pairs of quarks, 3 pairs of leptons, and they obey, I told you with lots of 3s, 3 sets of gauge symmetries, with the strong, the weak, and the electromagnetic interaction, which gives you the 3 bosons, and they interact with a non-zero Higgs field. If you want the mathematics of that, you can write it out. It still fits on one side of a sheet of paper, even if not on a T-shirt. And that's it. From that, you get all of particle physics. From particle physics, you get all of nuclear physics. It's how you build up your protons, neutrons, nuclei, and then atoms. And so chemistry follows on from this, and biochemistry follows on from that, and biology follows on from that. And everything springs out of this. Everything else is just stamp collecting. This is all you need to know. Everything else is just a matter of turning the handle. Of course, when I say everything else is turning the handle, that provides all the atoms and the material. It does not provide anything like love, beauty, affection, hate, value, purpose. All that set of values, concepts, are not provided by this. So at this point you can either say, this is the only thing that matters, all this love, hate, affection, warmth, they're just epiphenomena, they don't really exist. You can go the Dawkins route. Or you can say, this provides half of the things we experience. If we want to talk about beauty, ugliness, love, hate, we've got to look elsewhere. We're not going to find the answers in here. So this takes us to the idea that the book of nature, Augustine's been mentioned earlier, the 2 books you can read, there is the book of Scripture, in which God has revealed himself in one way, and there is the book of nature, in which he reveals himself in the other. And what can we learn, what should we learn from trying to read the book of nature? Augustine says, he's very specific. Can you ask for a louder voice than that? Why, heavens and earth shout to you, God made me. The logic goes that if you have creation in the Big Bang, or indeed if you have some final cause, then that implies a creator. Nothing shall come from nothing, nihil ex nihil fit. But it doesn't really stack up. Augustine is assuming that you are looking for God in his second line, God whom you want to discover. If you say, well, creation implies a creator because you can't just have something from nothing, then the logical next question is, how did the creator get there? Well, he was just always there, he's transcendent. Well, if the creator can be transcendent, why can't the creation? So I don't think you get a proof of the existence of God out of the fact that there was a creation, there was a Big Bang, and certainly there's an existence demonstration. There are enough physicists who work in this area who do not feel compelled to go out and subscribe to any deistic formula, that it's obviously not automatic. Another thing people try to pull out of this, and there's been a brief mention of this is the idea of the fine-tuning of the universe. The structure of the physical laws is set out by this symmetry-breaking business. The fine detail depends on the numbers of the way the Higgses interact with the particles and other things. And if you tot them up, there's about 25 of these numbers in all. They are what they are for some reason, and we don't know why. If they were anything a little bit different, then the universe would be a very different place, and it is kind of implausible that life like ours, I'm flattering us by calling ourselves intelligent life, could have evolved. If you just take an arbitrary set of numbers, then you get a universe either in which basically nothing happens because everything is too weak and it goes away, or in which everything happens at once and nothing has time to develop. It's a very delicate, carbon is such a wonderful atom, the way it can interact and do so much stuff. You don't have to make the attributes of carbon very different to completely destroy organic chemistry and make it like any other molecule. And the way we got here by successive supernova explosions and things, again, is very far-fetched. So people have argued that this implies that it could not have arisen by chance, and therefore there must be a reason for us being here. But this does fall foul of the anthropic principle, which basically says, look, we are here, we are asking questions, that we are in a universe which has enabled intelligent life to arise and questions its existence. So the fact that we are in a universe which allowed this to happen is not surprising, it is a given. You can't argue that its improbability means we must be some sort of special case. Can we learn the mind of God by studying nature? That's what Hawking hints at in his brief history of time. Huxley's famous counter to that argument is that the creator, if he exists, has an inordinate fondness for beetles, because there are thousands and thousands of species of beetles, more men than mammals or indeed humans. To be fair, this is a kind of paraphrase of something he was fond of saying. He did say stars and beetles, because there are lots of stars in the universe too. And it does seem, perhaps one could say there's a pattern here. If you were designing a world on which people could live, there would probably have to be beetles in it, as I expect they do something useful. But you shouldn't really need more than half a dozen different sorts of beetle to do all the beetly jobs there are. In the same way, we have these 24 sorts of fundamental particles, of which it seems we only need 3. They can stick together to make protons and neutrons and all sorts of other fascinating particles, rhos and omegas and lambdas and cascades and things. But we only need the proton and neutron, or maybe the pion. There is just, again, the periodic table with its 92 or whatever elements. Do we need ruthenium, lanthanum, erbium? We only need about half a dozen. So God does seem to be very profligate in what he does. We are used, when we look at something, to see it in terms of functionality. There is a chair, and the chair has a seat that you sit on. It has a support for your back. It has legs to keep it off the floor. Everything is there with a purpose. Even if you look outside, there is a tree, and a tree has a trunk to keep it upright and provide structure. It has leaves for photosynthesis. It has bark to allow moisture to travel up from the roots to the leaves, etc. You can look at a tree and see what every part of it does. But when you tree's been conditioned by evolution. If you look at the raw bits of the universe, the quarks, the leptons, the elementary particles, even the elements, and perhaps also the beetles, they don't seem to serve any purpose. When we look at things, we are tending to put our own value set onto them. So I do not think you can really psychoanalyze God by reading his works in the same way you can try and psychoanalyze an author by reading his books, or a painter by looking at his or her paintings. Indeed, if you can say something about the author, they're probably a fairly inferior author. So God remained ineffable. I don't think we can learn about him by studying his work in a sort of analytic way. So what can we do? Well, I'm not the first to quote Psalm 19. The heavens declare the glory of the Lord, and the firmament showeth his handiwork. And we don't understand God through that. We just look at it and say, wow. And Faraday said much the same thing. The book of nature which we have to read is written by the finger of God. So we should read the book of nature not for analysis, but for enjoyment, for appreciation. And what I want to explain to you today is that it's not just the heavens and the firmament and the sunsets and the mountain ranges and the oceans that declare the glory of God to us, and we look at and say, wow. We can look at the smallest and most fundamental scale is the basic way the universe works, and it displays an elegant simplicity which is really beautiful, the way it is symmetric and thus perfect, like the Aristotle and company wanted their orbits to be circular and perfect. And yet the symmetry is broken without breaking the symmetry that gives a prolific and rich behavior. So this is slide, it's the last slide, but it's one you've seen before, and I just want you to look at that and understand it and say, wow. Thank you.